All right, in this video, we're going to introduce the idea of implicit differentiation. So we have to talk about what the implicit part here means. We know how to differentiate things, so we'll start with talking about implicit versus explicit functions. Then we'll move on to the actual process of differentiation in this implicit idea. And really what we're talking about is we're going to be applying the derivative as an operation, which is kind of crazy to think about, but you'll see what I mean. Along the way, we're going to run into our old friends, the product and the chain rule, but we probably won't see the quotient rule. And so what we'll really do is try and answer that question, why no quotient rule here? But first, let's just start with the actual difference between the words implicit and explicit. We probably know what it means for something to be implicit or for something to be explicit. And when I say explicit, I don't mean like things like that. We're talking about saying something implicitly or saying something explicitly or something like that. So for explicit, normally we would think that if I'm being explicit about something, I'm saying it directly, right? I'm saying the actual words. Whereas if I'm being implicit about something, if I'm implying something, I'm kind of saying it without saying it, you know? We're not saying the actual words, but maybe we're getting a message across through subtext and stuff like that. So that's kind of the idea that we're going for in the math context as well. Something stated directly versus something stated indirectly. So we're going to talk about defining a function or a relation here, explicitly and implicitly. And here are two ways of defining the exact same relationship between variables x and y. You can see in the second one that we've just shuffled the terms around, right? There's no difference other than that we probably are more comfortable with the first explicitly defined version. And we maybe should start thinking about why is that? What about that form makes that comfortable for us? What do we like about explicitly defined functions? Probably it's that we can see the relationship directly. We know that if y is an output of x, we can see the exact input for x. We know what the rule is connecting that input to the output, right? We square x, we multiply it by 3, and then we subtract 10. Those are the steps that we take to get a y value. Whereas in the implicit defined version, we have that x and y work together in this equation in this way to equal 0. Y minus 3 times the x value squared plus 10 is equal to 0. That is a relationship between x and y, and it's the same relationship between x and y, but it's not stated as directly in terms of inputs and outputs. Cool. Okay, so what about differentiating these things to try and find the derivative of y with regard to x, or maybe we'll just call that y prime? Doing that explicitly is super easy, right? Y prime, we can use the power rule on this and say this is 6x minus the constant 10's derivative, which is 0. If you wanted, we could go ahead and write out all the different rules that we're using here, but we'll just say 6x. Easy enough. What we want to know then is how do we differentiate this thing implicitly to try and get the same derivative, but we'll differentiate this version of it instead. It's the same relationship between x and y, so it should give us the same derivative. The main idea here is that we're going to be using the derivative as an operator. I'm not going to get too much into what it means to be an operator in this video because that's a little bit beyond what we need, but we're going to think about some sort of an equation, right? Like 4x squared plus 6x minus 10y equals 15 plus 7x over 3. Here we go. What we can do is say, like, maybe I don't want fractions in here. And so we can multiply both sides of our equations, both sides of our equation by 3, right? And then we end up with 12x squared plus 6x minus 10y equals 45 plus, I forgot to actually multiply. 12x squared plus 18x minus 30y, there we go, is 45 plus 7x. And then if you also wanted, we could say, like, what if we just combined our x's on one side and y's and constants on the other? We can go ahead and we can subtract 7x from both sides, right? And we can add 30y to both sides. This isn't news, but this is what we mean. We want to be able to do the same thing to both sides. And what if we use the derivative in that way? What if we differentiate both sides? That should make a bit of sense to us. If we have two things that are equal, then the rates of change of those things should probably be equal, right? So that's what we're going to do. We're going to go ahead and we're going to differentiate both sides of this equation with regard to x. So we'll say the derivative of y minus 3x squared plus 10 equals the derivative d over dx of 0. And now all of these things we can do, although there's a little bit of something going on right here with this term. But let's just start from the right. The derivative of 0, that's pretty easily going to be 0. If you want, we can break this apart into three different pieces. We say this is the derivative of y minus the derivative of 3x squared plus the derivative of 10, right? The derivative of a sum is the sum of the derivatives. That's a property we've been using. The derivative of 10, that's going to be 0. The derivative of 3x squared, well, that's just 6x. And the derivative of y, that can be kind of tricky to think about until we realize that that's what we're trying to find, right? We're trying to find dy over dx. Or if you wanted, you could call that thing y prime. And now we can just solve for dy over dx, and we get that the derivative of y with regard to x is equal to 6x, just like we had earlier. So we get the same answer here using this idea of applying the derivative as an operator on both sides of our equation. All right, here's another basic example that we could look at. If you wanted, we could go ahead and shuffle this thing around and say, well, y is equal to 1 minus x squared minus e to the x. And then we could find y prime normally, right? Not that bad. But let's use this idea of implicit differentiation, and let's say that for y plus e to the x equals negative x squared plus 1, let's go ahead and apply the derivative to both sides. Let me give myself a little bit of room here. There. And now, again, we can break this thing up and say, well, really, this is the derivative of y plus the derivative of e to the x, and that's going to equal the derivative of negative x squared plus the derivative of 1. And each of these we can find, right? We know that the derivative of y is dy over dx, or maybe if you want, we can use y prime. That's fine. Plus e to the x equals negative 2x plus 0. So we've got y prime equals negative 2x minus e to the x. And that's exactly what we would notice here, right? It's the same thing. So the question is, like, who cares, right? Why would we even do this? I mean, for these, we may as well just solve for y and differentiate these things normally. Or maybe I'll put that in quotes, like normally. It's only normal because that's what we've started off with. That's what we know now. But why would we change a good thing, right? If it's not broken, don't fix it. What we'll notice, though, is that y could be an output variable of an input x, but it doesn't have to be specifically. What does that really mean? It means that we might not actually have like a function written this way, f of x equals whatever, some explicitly defined thing, right? And we might not even just have a shuffled up version of this because we might not actually have a function. For instance, this is probably something that you've seen before. X squared plus y squared equals 0. Hopefully you know what this graph looks like. This is the unit circle. It's an equation defined in this way, but I hope you notice that this is clearly not a function, right? The vertical line test doesn't work. It's got multiple points that pass through some specific vertical lines. If you try and solve for y, you're going to get y squared equals 1 minus x squared, and that means y is going to be plus or minus the square root of 1 minus x squared. You actually get two functions. One of them is this upper square root of 1 minus x squared, and the other is this lower square root of 1 minus x squared. So this is an example where we could kind of split this up into multiple functions, but you might not always actually get a function. All this to say that we might have to apply the chain rule here, because if y is an output variable of an input x, then when you do something to y like this, we square it. What we're doing is composing a function inside of another function. This is the power rule applied to some function of x. So we might have to apply the chain rule here. So if y is composed inside of anything, power functions, exponentials, trig functions, square roots, anything else that we've seen, we're going to need to apply the chain rule, because that's really a function inside of another function. That's going to be not too bad to see, because it's going to follow the idea of the chain rule. For instance, if we go ahead and look at d over dx of y squared, just like we did earlier, we'll notice this variable is not the same thing as this. And just like when we had that variable substitution in the chain rule with using u's and stuff like that, that means we'll have to use a linking derivative. We'll multiply the derivative with regard to y times the derivative of y with regard to x. So this is how we're going to do things. We'll treat y like a variable, differentiate that portion, and then add on that derivative of y afterwards. That's how multiply on. What am I talking about? That's how the chain rule is going to work. All right, so here's an example. Let's go ahead and find y prime or dy over dx for this curve that we have defined by this equation. So we'll start with just writing out the derivative with regard to x of y squared minus the derivative with regard to x of sine of y plus the derivative with regard to x of tangent of x, and that's equal to the derivative with regard to x of 0. I'm going to apply the derivative to everything on each side. Now, what you'll notice is that right here and right here, we have these y inputs. That means we're going to need to use the chain rule here. We can differentiate 0 pretty easily, and we can differentiate tangent of x pretty easily. I know that the derivative of 0 is 0, and I know that the derivative with regard to x of tangent of x is just going to be secant squared x. But now, for these ones, I'm going to have to rewrite this as the derivative with regard to y of y squared times the derivative of y with regard to x. Minus, for the sine term, we'll have the derivative with regard to y of the sine function times the derivative of y with regard to x. If you want, we can use y primes here. So we end up with 2y y prime plus, minus, I forgot that sign was there, minus cosine of y times y prime. And then we have plus secant squared x equals 0. Now what we have to do is just solve for y prime. I'm going to take these terms with y primes and I'm going to leave them on this side. And I'm going to move that secant squared over. So I'm just isolating my y primes. If I do this, I'm going to notice that y prime is a common factor. So let's just factor out y prime. And now we're left with 2y minus cosine y. If y prime's not a common factor when you've done this, that means you haven't moved all the right terms around. So again, shuffle them all up until you only have y prime terms on one side, and then you're guaranteed that y prime is a common factor. Now we've got that y prime equals negative secant squared x divided by 2y minus cosine y. That's pretty ugly, but whatever. That is y prime, or if you'd rather, dy over dx. Same thing. So we can apply the chain rule here by just stepping through those linking derivatives. The product rule, okay, again, note that y is, or at least it could be, an output variable for an input variable x, and that means that when we have terms with x's and y's in them, we have products of functions, because y in and of itself is its own function, or at least output. I don't want to say function because, again, we might not have an actual function. We might have like a circle where it breaks the vertical line test. But outputs. So we have different outputs multiplied by each other. So we're going to have to split them up and apply the product rule. Find the derivative of each piece individually and piece them all together. Here's your example. So notice in these two terms, we've got x's and y's floating around. When we differentiate these, I'm going to give us lots of room here. we're going to have to apply the product rule. We'll split these up as naturally as we can. The easy enough way of doing that is to say something like u is equal to y and v is equal to the rest of the stuff. U prime then, this is the derivative with regard to x of y, so it's not going to be 1. This is really du over dx or dy over dx. I'll call it y prime. And v prime is 3x squared, just like we expect. Then I'll use a's and b's over here. We'll split this up in the same kind of way. A is equal to y, and now b is equal to e to the x. A prime then is y prime, and b prime then is still e to the x. Now our product rule says, let's put all this stuff together. So we have 3x squared y plus x cubed y prime minus all of this stuff, y e to the x plus y prime e to the x equals 0. I'm going to go ahead and distribute my negative through here. And what we really have now is 3x squared y plus x cubed y prime minus y e to the x minus y prime e to the x equals 0. Again, I'm going to look at my terms that have y primes in them, keep them on one side, and put everything else on the other. Or maybe I'll just move those around. It doesn't really matter. So I've got 3x squared y minus y e to the x equals y prime e to the x minus x cubed y prime. And now you can see that if y prime is the common factor, the thing that's left over is going to be this e to the x minus x cubed. So hopefully we can just do this division. 3x squared y minus y e to the x over e to the x minus x cubed equals y prime. Again, that's just by factoring out y prime. And now we can divide. But there's our derivative, dy over dx. That's not too bad. What you'll notice is that these derivatives have x's and y's in them sometimes. That's a little bit different than what we're used to. So these derivatives may not actually be perfect like functions of single variables or something like that, because we have to take in both coordinates x and y sometimes. All right, that's the product rule. Okay, so here's the question. Why do we not see the quotient rule? We kind of subtly already talked about this, but let me give you an example of where you would expect some quotient rule to show up. Maybe we have like x squared plus 1 divided by y plus y squared over e to the x equals 10. Doesn't this seem like we should be using quotient rule on these, right? Differentiate all these terms, get those quotient rules floating around. Notice we have an equation, so we can just do stuff to both sides, right? So maybe what I'll do is just multiply by y e to the x on both sides. And if I do that, then what I have instead is x squared plus 1 e to the x plus y cubed, the e to the x in this one cancels, and I've got a y cubed now, equals 10y e to the x. No more quotients. Because we have an equation, we can just clear out denominators whenever we want. So you could use the quotient rule on this if you wanted, right? You could go ahead and just differentiate things directly. Everything works out fine, but you don't have to. You never have to worry about division. You can just multiply those denominators out to get rid of them. Okay, a couple of notes and observations while we wind this thing down. Sometimes I've seen it in textbooks and in other people's notes and stuff like that, that they'll look at an equation like 10y plus 4e to the x equals 7, and they'll rewrite this as 10y of x, right? To really force the idea that you've got a function here. I'll be honest, I don't love this. I think that looks like multiplication to me. And so that looks like I would use a product rule on that instead of a chain rule. So what I would rather is if we all got pretty comfortable with just seeing that d over dx of 10y has to be d over dy of 10y times dy over dx. The derivative of that function with regard to the variable that we care about, and then multiply this linking derivative together. Use the chain rule. The chain rule always acts in the same way. You're going to differentiate things with respect to y and then multiply by that derivative dy over dx. That's always going to be the same thing. The product rule is a little bit more annoying to set up because you have more choices to make. You have to think about what your pieces are, and it might act a little bit differently depending on the way that your equation's set up. But the chain rule is always going to be the same. A lot of the relationships that we'll look at aren't actually functions, and that means that we can differentiate curves that aren't functions, right? That means we could look at some sort of a curve that looks like this, and we could find a derivative, and maybe what that means is we could find slopes of tangent lines. Oof, that's not a very good straight line. We'll look at that in our next video. We'll try and actually use this to do the things that we expect derivatives to do. I'm going to do the classic math prof fix and just make my point really big so it does look like a tangent line. I think using this proper notation is really helpful because then we can see this difference in the variables. So get used to using this differential notation, d over dx, as a derivative operator on our equations, and hopefully that's helpful. That should be pretty good, I think. We'll take a look at some examples and actually using this in our next video, and then we'll look at some more like physical applications called related rates in a little bit. So good luck as you move through this.